So next here we're going to talk about the equilibrium constant, which often is called KEQ, but your book calls it K because, you know, there aren't enough Ks, right? We're always so creative with these notations. What should a constant be? Well, you can't spell constant without K. Let's go with K, right? So it's another one. So keep in mind that this chapter, this is not your reaction rate constant, this is equilibrium constant. And in my notes, I'll often go with KEQ, or there's a few other notations I'll show later. And your book will actually go into some different notations like KA and KB and KSP. And I think there's one or two others as well in 223. And they're all equilibrium constants. It's just for different types of equilibrium systems. They start stacking on different stuff, but they're all just types of KEQ, you know, equilibrium constant. So it's nice to have that little subscript because there's so many Ks. So that's what I'm going to try to do. All right, so as we talked about in the last video, you know, it's a dynamic process, but some things stay stationary. For example, concentrations of our reactants and products are unchanging. Once we reach equilibrium, they stop changing. So there must be some sort of constant ratio of our concentration of products over our concentration of reactants. This is a very rough idea I'm sketching out at the beginning. We'll get more detail in a second. But we have to have this constant ratio, and that's what KEQ is. It's just that ratio. So there's a constant ratio of these concentrations. Well, it's a constant, so let's just put a number to it. All right, so there's a little more detail than just concentration over concentration, but it's that general idea that we're going to expand on. And so if we look at our generic system, A moles of A plus B moles of B become C moles of C and D moles of D, and it's reversible, so it's going to have an equilibrium. We look at this, and we go, what an exciting chemical equation. I know, haven't seen this one before, right? But now we're going to look at it in terms of equilibrium. And so our general expression is products over reactants, but our stoichiometric coefficients become exponents on our concentrations. So if, you know, if it's just 1 mole of something, then it's just concentration. But if it's 2 moles of something in our equilibrium, then it's concentration squared. Or if it's 3, concentrations cubed, so on and so forth. And so we'll have concentration of product C to the power of lowercase c, our concentration of product D, whatever molecule or compound that is, to the power of whatever its stoichiometric coefficient is. And then we do the same with the reactants on the bottom. So A and B show up with lowercase a and b exponents. So this is kind of the general formula. You could have more, but this just shows, you know, a framework you can build on in any situation. Like this is the blueprint. So details fall into place that kind of go around here. So we're not just always going to be making C and D out of A and B. We'll have other reactions, but this is, you know, just a good way to remember it, to show basically every situation. There's no other detail to show besides this. All right, so let's get a little more specific now. So if we know all of our concentrations and we know our system, we can calculate KEQ. We can calculate what the constant is. And later on, if we know what KEQ is and we know what the system is and we know what we start with, we can find out where we reach equilibrium, what that's going to be. But that's the end of the chapter. That's actually really complicated. There's a lot of math involved with that. This isn't too bad. So if we know our concentrations at equilibrium, if we just let it reach equilibrium, we don't see any change in our concentration, so we know we're there, and we just start measuring how much of each substance there is, we can calculate K. And so for example, if we have a situation where we're mixing H2 gas, I2 gas, it's going to form equilibrium with HI. And so for every H2 and I2 that combine, we're going to get 2 HI. So we get this equilibrium process, but HI can also collide into itself, another HI, and reform our original reactants. So it is reversible. It's all in the gas phase. So they're all bouncing around. And so if we have a situation, we let it reach equilibrium, we measure H2 and I2, and we see that they're each 0.1 molar. And we see that HI is 0.7 molar. So this is an equilibrium that will say, you know, it strongly favors the products. There's a higher concentration of products at equilibrium than reactants. But that's not where we're going with this. We know all of this, we know this. Can we calculate KEQ for this system? And the answer is yeah. So first let's just write the general expression. So I'm like, all right, so KEQ, It's going to be products. Okay, well I have two HI, so it'll be concentration of HI. And then I have to square it. All right, that's all my products. So now I divide by reactants. There's only 1 mole of H2 involved, so that's just concentration of H2. Only 1 mole of I2 involved, so it's just concentration of I2. Okay, and I know what all those concentrations are at equilibrium. And so I just plug these numbers in. And so I have 0.7 squared over 0.1 times 0.1. So both of these were 0.1. Put that underneath. Now one thing I want to point out here, before we do the quick calculation, I didn't write any units here. So KEQ is a unitless constant. So it's a little different than the reaction rate constant, where it varied depending on the situation. You have all these units and you could have a question about it or something, and what's the unit of a second order reaction, and so for the rate constant of a second order, blah blah blah. What's the units of a equilibrium constant? Every single situation, unitless. So all that matters, I could have recorded these in ppm or milligrams per kilogram. That's a joke, same thing. Molality, doesn't matter. As long as all the units match, I'm gonna get the same number at the end, so we don't worry about units. KEQ is not unit dependent as long as all the pieces have the same units. So what we're gonna do is just the math, and it comes out to be 50. No units, just 50. So we'll make a little note here. Unitless. All right. And I'm thinking that SmartWork has a couple of questions that kind of dress this up a little bit, but it's the same underlying concept. So you just got to figure out what the concentrations are at equilibrium, and that's where they might get a little fancy. Maybe you start with a certain amount of stuff and then they tell you how much of something else there is at equilibrium, and you got to figure out everything from there. That's about as extreme as you can go with this, but it's just a little detail on top of this kind of key thing. So first off, be able to write the equilibrium expression, and then plug your numbers into it and solve. So this is a big first step. This is a very key idea throughout the whole chapter. So make sure you understand that. And then being able to plug in and say, oh, okay, so it's 50. And we're gonna mess around with these equilibrium constants a lot more at the end with a lot more depth. But for now, there's just observe it at equilibrium, what's KEQ. Later on, it's gonna be what happens if we poke a system at equilibrium, what happens if we just throw stuff together, where does it land at equilibrium? By calculation, not measurement. And that's trickier.